Hello friends, welcome to all. Today we will discuss about integrator circuit using op amp. It means operational amplifier. So in previous lecture we have studied about summing amplifier, subtractor. It means differential amplifier. So in all these applications, op amp is used in inverting mode or in non-inverting mode. So we can use op amp in different mode: inverting, non-inverting, or differential. So there are the mostly three modes are there. Today we will discuss about integrator circuit. So in that case we will use op amp in a inverting mode. So first of all we will draw the circuit of integrator. So this is the op amp. Okay, here is minus and plus. Output is taken from here, and in feedback there is a capacitor. It is also known as feedback capacitor, and input signal is given here. This is R1. Here is V0, it means output voltage, plus VCC and minus VEE. Here is a V1 and V2. Here is IF and input bias current IB. And here is I1. So this is the circuit diagram for integrator circuit. From this circuit we can say that this operational amplifier is used in the inverting mode because input is given in inverting terminal and non-inverting terminal is connected to ground. It means operational amplifier is used in inverting mode. And one more thing is, in feedback there is capacitor. On the other way, in other circuits generally a resistor is there in a feedback, but in an integrator circuit there is a capacitor CF. So this is the circuit diagram of integrator. So simply this circuit can be obtained by replacing the feedback resistor RF in inverting amplifier with feedback capacitor CF. Okay. Now how can we find the output voltage mathematically? So referring to this figure, applying the Kirchhoff's current law at node V2. Okay, so here is I1, IF, and this is the IB, almost 0. Okay, so by applying KCL, it means Kirchhoff's current law at node V2, then we get I1 is equal to, at this node I1 is equal to IF plus IB. Okay, IB plus IF, it is algebraic sum. Now we know that the input bias current is very small, and it is negligible as compared to IF. So we can write I1 is equal to IF because IB is negligible. Okay. Now, what is the basic relation between the current through the and the voltage across capacitor? So we know that I is equal to C dV by dt. This is the basic relation for current through capacitor, it means IC, and voltage across capacitor VC. Okay, so this is the basic relation. Okay, now in case of integrator, IF is equal to ICF. So we can modify this equation as I1 is equal to C into dVc by dt. In place of IC, we can write I1. Okay. But I1 is equal to, I am writing here, but I1 is equal to VIN minus V2 upon R1. Okay. Here we can say VIN and here is V2. So VIN minus V2 upon resistance is R1. And what is the voltage across capacitor? That is VC is equal to V2 minus V0. Okay, here is V2 and here is V0. It is V2 minus V0. Now, substituting these values in this equation, so we can write in place of I1 we can write VIN minus V2 upon R1. It is equal to CF into d by dt V2 minus V0. Okay. By putting these two values in this equation, we can write this. Now, using the concept of virtual ground, we can write V2 is equal to 0 because of virtual ground. So, put the V2 is equal to 0 in this equation. VIN upon R1 is equal to CF d by dt minus V0. This one is 0, so in the bracket only minus V0 will be there. Now, output voltage can be obtained by integrating the above equation. Okay, we have to find this V0, but it is under the differentiation of time d by dt minus V0. So if we have to obtain this V0, then we have to integrate this equation. Okay, so by integrating above equation, we can write V0 is equal to, this one will be in the denominator, okay, minus 1 upon R1 into CF and integral VIN dt plus constant C, and the limit will be 0 to t. Okay, so this is the output voltage. So we can see in the output voltage there is an integration of input voltage VI. It means this circuit works as an integrator circuit because in output there is a integration of input. Okay, so this way we can explain the integrator circuit. Now, if we apply the square wave in the input, what will be the output? See, if we apply the square wave input, then we can get triangular output wave. Okay, and if we apply the sine wave input, then output will be cosine wave, because of integration of sine will be cosine. Okay, so this way we can get the integrator output of input voltage. So this is the basic circuit of integrator. Now we will discuss about one more application of operational amplifier, that is differentiator circuit. Okay, so what is differentiator? A differentiator circuit produces differentiated version of the input voltage applied to it. This process is exactly opposite to integrator, that we have already seen integrator. So this process is exactly reverse or opposite to the integrator. So components connected in the integrator circuit have interchanged their positions to produce a differentiator circuit. Now we will see circuit diagram, then we can say that how the components are interchanged. So first of all, here is the one op amp, here is capacitor, minus and plus. Here is output, and in feedback there is a resistor RF. Here is C1. This one is VIN, and this is capacitor current IC. Here is feedback current IF. This one is V1, V2. Okay, here is V0. So this is the basic circuit diagram of differentiator. Now we will compare this with a integrator circuit. Here we can see the circuit diagram of integrator circuit. So we can say that these two components R1 and CF are interchanged, then we get this circuit. So capacitor is connected here and this resistor is connected in feedback. So capacitor will become C1 and the resistor will become feedback resistance RF. Okay, so we can compare these two circuits. Okay, just by interchanging these two components we can get differentiator circuit. Now we will discuss for expression of output voltage. Now here we have assumed that ideal op amp is used. It means this voltage V2 is equal to 0 and input bias current is also equal to 0 because of ideal op amp. So we can write here at node V2, we can write IC is equal to IB plus IF. Okay, IC is equal to IB plus IF, that is Kirchhoff's current law applies at this node. Okay, so we get this formula. But we know that IB is equal to 0 here. So we can say that IC is equal to IF. Okay. Now we know the relation. We know that IC is equal to C to dVc by dt. Now voltage across C1 is given by Vc is equal to Vin minus V2, and substituting to the above equation, then we get IC is equal to, see, IC is equal to IF, so we can write here IF. IF is equal to C1 into d by dt. In place of Vc, we can write Vin minus V2. Okay. Now obtain the expression for current IF. Okay, so we can write IF is equal to V2 minus V0 upon RF. Okay, this will be the equation for current. Now we know IC and is equal to IF. Okay, IC is equal to IF. Therefore we can equate these equations. Equation number 2 and 3. Okay. So by equating equation number 2 and 3, we can write C1 into d by dt Vin minus V2 is equal to V2 minus V0 upon RF. Okay, so this way we can equate equations. Now by using the concept of virtual ground, because of virtual ground, we can write V2 is equal to 0. So C1 d by dt into Vin is equal to minus V0 upon RF. So from this equation we can find V0. Okay, so V0 is equal to minus RF into C1 into d by dt Vin. Okay, so this one is the formula of output voltage of differentiator circuit. Here we can see that the output of this differentiator circuit is the differentiation of the input voltage. So this way we can explain the differentiator circuit. Now if we apply the square wave at the input, then we can get spikes at the output or triangular spikes in the output voltage. So this is the basic differentiator circuit.